Sorry about that. My controls seem to have disappeared. Again, my apologies. One moment, please. They were there just a minute ago. My apologies, Dr. Major.
Not a problem, still here.
All right, here we go. All right. The controls are over to you. You can go ahead and share your screen and begin whenever you're ready.
Great, can you hear me okay?
Yes.
Lovely. Okay, so we've got a lot to talk about today. So as mentioned, my name is Manny Major. I'm coming from the Northwestern University. We'll be talking today about statistics you need to know, and probably a few things you don't need to know or didn't want to know. The purpose of the lecture is twofold. First, what I'm planning on doing is providing essentially a baseline knowledge of biostatistics. And second of all, what I'm trying to do is get you as excited about statistics as I am. If I fail in doing so, I will pay for your student loans. Please notice the disclaimer on the first slide there. Okay, so just to let you know where I'm situated, as mentioned, I'm coming from Northwestern University. I'm at the Prosthetics-Orthotics Center, also affiliated with the Jesse Brown Biomedical Center. You can see a nice photo of Chicago with our C next to the building there. There's my building, and coincidentally, there's my yacht. Just kidding. All right, so to give some information on what we'll be talking about today, I've got a few chapters I want to go through. The first thing I'm going to talk about is study designs and levels of evidence. Second of all, then measurement scales. We'll get into the idea, the concept of normality and some descriptive statistics. We'll then work our way into statistical analysis design, speak a little to alphas and betas and error. And then I'll wrap things up with how you can be a savvy consumer of research literature, or essentially how to evaluate a research article. So why statistics, just to start? So essentially what we're trying to do is capture some information in the context of natural variability, right? We have a need to predict future outcomes based on previous experiences. However, the lived experience bombards us with noise and is inherently variable. Statistics essentially is the science of collecting, organizing, summarizing, and analyzing information to draw conclusions or answer questions. So essentially, we can prove nothing, but with statistics, biostatistics, and statistical analyses, we can merely suggest phenomena with some level of confidence. So why do we do this? One is engaging in the research process. That's exploring the probability of arriving at certain outcomes. We may be looking at studies that are evaluating diagnostic potential, group differences, and predictive models. And as I mentioned before, to be a savvy consumer of research literature. So that might be reviewing publications, peer-reviewed or other, in order to keep yourself current on new findings. And in addition to that, what I'm trying to do today is give you some knowledge on how to identify poor study designs, any inherent bias in the study, and even misinterpretation of the study results. And then finally, what I'm not going to go into too much is evidence on, some information on evidence-based practice and the art of making informed decisions, and how the information that you're receiving today can help you make those informed decisions. Okay, so for our first chapter, we're talking about study designs and levels of evidence. And the reason I bring this up to start is because statistics does not happen in a vacuum. Although I can say from personal experience, it does happen sometimes in a windowless office space. All right, so you might have seen this before. This is the hierarchy of levels of evidence. What I like about this particular pyramid is that on the left-hand side, what you can see are different databases and resources that you can use to help you find this information. What I'm going to be focusing on today primarily is the unfiltered information. So I'll give you some description of that primary or original research. But I won't be talking about necessarily secondary research. This is the synthesized research. It's essentially taking all of that primary and original research and filtering it such that you can then receive an interpretation of the body of literature. In addition to that, what I'm not going to be talking about at all here is animal research and in vitro research, but it is at the base of that pyramid. All right, so first let's start off with a few definitions. All right, to identify if your study design is experimental or non-experimental. So for experimental, this is researcher-controlled manipulation of independent variables, that's your explanatory variables, to assess an effect or effects on some dependent variable, that's your outcome or response. It's really research that is designed to answer cause and effect. So for instance, you might be separating a cohort of individuals or patients into treatment A and treatment B and trying to identify the outcomes between those two different treatments. Then there's non-experimental. This does not require any manipulation of independent variables. Really, it is meant to be an observation of phenomena or description or to assess relationships. And that could be either retrospective or prospective. In this case, you might be looking at that very special cookie, sort of interested in case designs, case studies, and case reports. So to give you a few examples here between experimental and non-experimental, just to set more context, experimental might be, for example, randomized control trials, pre- and post-test controls, time series, repeated measures. And non-experimental, what tends to fall into that group are case reports and case series, case controls, cohort and epidemiological studies, as well as that filtered analyses I talked about before, like meta-analyses and CABs. All right, so giving a bit more definition to case reports and case series. A case report or a case study is a systematic documentation of an individual's condition or response to treatment. It could also include a study that is focused on a group, an institution, or even a social unit. Case series essentially is really just an extension of the case study involving observations in several similar cases. Now, they have advantages and disadvantages. There's the advantage of totality, right? In this case, you have the flexibility of complete reporting of an individual's condition and outcomes. And this might include their physical status and even their psychological status. Now, there is the disadvantage of poor generalizability. Oftentimes, these are very unique cases, and they're difficult to replicate. In addition to that, they are the least rigorous of all the studies, and there's many opportunities for bias, and that's something very important to keep in mind. However, overall, they allow for contributions to both clinical knowledge and practice, right? You get the opportunity here to share clinical experiences. You can also illustrate the use of evidence-based practice. So, talking about case control and cohorts, case controls are retrospective. It's when groups of individuals with and without a condition are compared to determine if they have been exposed to a presumed cause. So in this case, you are starting the study by identifying your groups, your controls, and your cases. You're working backwards to determine what the exposure is. Have they been exposed or they have not been exposed? Cohorts are slightly different. Cohorts can be prospective or retrospective. In this case, you are tracking groups of participants of differing exposure to determine which group is more likely to develop the condition. So for instance, you might be identifying a cohort. You then identify their exposure, whether they have been exposed or not exposed to the presumed cause, and you're following along to determine what their outcomes are. Either they develop the condition or they do not develop the condition. In the retrospective concept of a cohort study, you're actually starting at the very end. The condition is already developed, and you're working your way backwards, then identify the exposure from that particular cohort. The main distinction between these two, and it's important to keep in mind, is that for case controls, the condition is known, whereas for cohorts, the exposure is known. Now, again, advantages and disadvantages. There's the advantage of sampling. Case controls, the sample is relatively easy to gather for studying rare conditions, because you're already identifying those conditions. For cohorts, you have the ability to sample based on exposure, and then you're able to establish a temporal sequence. Now, there is the disadvantage of challenges to addressing research questions. So for case controls, there is the uncertainty in temporal relationships between the exposure and the condition. And for cohorts in the prospective case, they're not really useful for studying rare conditions. Oftentimes, if you are studying rare conditions, requires a lot of samples and a lot of time. All right, so to finish up, we'll talk about randomized control trials. Really is considered the gold standard for prospective experimental studies. These studies are designed to determine the outcomes from a particular treatment. They are random because it's a random allocation of participants into treatment arms, either the treatment or control groups, and there is a control. The treatment is compared to some control condition, either placebo or some other standardized treatment. In addition to that, they can be blinded. This random allocation between treatment and controls, that allocation may be unknown to one or both the investigators and or participants. But in this case, for this particular study design, you have random allocation separated into two groups. You might then take a pre-test measurement, apply the intervention, and then take a post-test measurement. Now again, advantages and disadvantages. There's the advantage of control and reliability. The independent variables, that is the treatment, is manipulated through very careful control, and the dependent variables are collected under very controlled conditions. There is the disadvantage of resources and ethical considerations. When they are done well, they are costly and oftentimes very time-consuming. In addition to that, there's oftentimes ethical considerations of applying a control that demonstrates less favorable outcomes. In this case, it may not be ethical to continue applying that control case when, again, it is not as favorable as the intervention. All right, to wrap up this section, we'll talk about clinical research or generating knowledge. Really, it is a process that proceeds in a systematic way to examine clinical conditions and outcomes, to establish relationships among clinical phenomena, to generate evidence for decision-making, and to provide the impetus for improving methods for practice. And of course, research must be empirical and critical, and the results must be observable, documented, and validated. The instruments that we use, they capture both quantitative and qualitative information, but they have to be accurate and reliable to measure those outcomes. When we're deciding on a statistical approach, there's a few things we need to consider in this case. One is the research question and the associated hypotheses of that study. The study design, is it experimental or non-experimental? Then the measurement scale. Is it nominal, ordinal, interval, or ratio data? Now this is important because that measurement scale or the data type will determine its treatment. So let's jump into that. So now we'll discuss measurement scales, a little bit on the concept of normality and descriptive statistics. You might be familiar with this. There are different levels of measurement scales or different data types. At the very bottom, we have nominal. These numerals denote categories. It might be sex, diagnosis, blood type, but the categories themselves do not represent ranking. Moving up, we have ordinal. Now, in this case, the number indicates the rank order. This might be a pain scale, for example. The value indicates a greater than, less than relationship. Then there's interval. Now the numbers have equal intervals, but no true zero. An example of this is temperature. Right? You can have negative temperature, you can have positive temperature, but 0 degrees Fahrenheit doesn't mean that there is no temperature or no heat. And then finally, we have ratio. Now the numbers represent units with equal intervals and a true zero, such as weight. If we have no pounds, that means we have no weight. A quick note on this, on the distinction between ordinal and interval data. So the difference between a 3 and a 4 in the pain scale might not mean the same as between a 7 and an 8. It might not mean the same across participants or patients, and it might not mean the same within the same participant. Whereas the difference between 10 degrees and 20 degrees Fahrenheit is the same as between 50 degrees Fahrenheit and 60 degrees Fahrenheit. That difference is always going to be 10 degrees Fahrenheit. I bring this up only to emphasize that ordinal data just represents position, but it doesn't represent quantity. Keep this in mind as we start to go through some of the data analyses. Okay, so now let's talk about data normality and this question of distribution. You want to know, is the data normally distributed? When I'm describing normal distributions, what I'm referring to is this Gaussian distribution of group data. You might have seen this. It is the characteristic bell curve. You have some central tendency and you have a dispersion. Most of that data, most of those individuals and those samples are grouped within that mean or grouped around the mean in this case. As they begin to trail out, as the standard deviation increases, you get less and less individuals, less frequency in those tail ends. And of course, the data distribution is often visualized through these histograms you see on the bottom. And as I mentioned, it follows that characteristic bell curve. The central tendency in this case is the mean, and you have an associated dispersion. That's your standard deviation. So you might see data that is represented or visualized in this way. In this case, you have treatment effects of treatment A and B. You then have a mean for A and B, and you have some error bars associated with that. Those error bars denote your standard deviation. I'm not giving too much math in this presentation, but I just want to demonstrate here that these are the equations for calculating the mean and standard deviation. What I'd like to point out is they are a function of sample size. Okay, so let's talk a bit more about the question of distribution, how to identify when distributions are not normal. So what happens when that assumption or normality is actually questioned? Now, distributions may be biased, they may be skewed, or they may even be multimodal, as you see on the bottom there. You have positively skewed, negatively skewed, you even have J-shapes, and you might have a bimodal distribution. What's nice is that we can actually test these assumptions with common statistical analyses. Those include the Shapiro-Wilk test and the Kolmogorov-Smirnov test. Caveat, just to keep in mind, is that small sample sizes does not necessarily mean normality is violated. I'm going to be talking a lot about parametric statistical analyses and non-parametric analyses. Now, parametric statistical analyses assumes data normality. And in this case, that is critical to not produce misleading results. Whereas the use of non-parametric analyses makes no assumptions on the distribution. These are just two groups of statistical analyses in this case, right? And why it is called parametric is that means it makes assumptions on the parameters of your data distribution, whereas non-parametric makes, again, no assumptions on that distribution. Now, quick caveat, just something to mention, there is a bit of controversy as to whether ordinal data, as I mentioned before, should be treated with non-parametric analyses. This really is dependent on if the distribution is approximately normal. And this can happen sometimes if you have measures of many, many ranks. So rather than a 0 to 10 on the pain scale, you might have 0 to 250. You have increased resolution in that case. Okay, so let's give an example of descriptive statistics, or how to communicate characteristics when you have parametric and non-parametric analyses. So this idea of normal versus non-normal. So again, normal distributions, those that are considered approximately symmetric, those apply to parametric statistical analyses. Whereas when you have identified a non-normal distribution, they then require non-parametric statistical analyses so as not to produce misleading results. So just an example here. If we're trying to describe characteristics of a data set, if I'm using parametric analyses, I need to describe the mean or the central tendency, and that dispersion is then characterized with the standard deviation, the standard error, or the range. And again, a graphical display would look like something on the bottom there, as I mentioned before. If I'm using non-parametric analyses, now I need to shift it slightly. So that central tendency needs to be described through the median rather than the mean, and the dispersion in this case is the interquartile range or the range itself. You might have seen box plots, as you do on the bottom right there. It's a way to graphically display information that is non-parametric or non-normally distributed. You have max and mins, you have your interquartile range, and your median, and then maybe even a few outliers. And we'll talk a bit about outliers further along. Okay, now that we've set the scene, we've set a bit of context, let's get into statistical analysis design here. All right, so start off with a statistical approach, or selecting the correct path to analyzing your data. We need to start off with understanding the research question and hypotheses I mentioned before. Hypothesis testing is a procedure that is based on sample evidence and probability used to test statements regarding a characteristic of one or more population. You need to ask yourself, what is the primary aim of this study? So for example, does treatment A affect a specific outcome compared to a placebo? That should be affect, not effect there. We're interested in assessing the main effect of treatments on outcomes in this case. The null hypothesis then is that there is no effect of treatment on outcomes. That is to say, there's no difference between treatment A and the placebo. Then it follows that the alternative hypothesis is that evidence is there to suggest an effect of treatment on outcomes. So now we need to ask about the study design itself. How are we actually assessing this? So the 6 questions you need to ask: how many independent variables are there? How many levels for each independent variable? How many groups are being tested? How are the subjects assigned to groups? How often are the observations made, and what is the temporal sequence of interventions and measurements? These will become a bit more clear as we start to go through the different statistical analyses. Okay, let's start off with the first example of a statistical analysis in which we want to assess frequencies. So we're looking at proportions and categories. This is referred to as the chi-squared analysis of homogeneity. What we're looking to do is assess if different populations have the same proportion of individuals with some characteristic. So, for example, you may be asking, what is the proportion of patients with normal or high levels of cholesterol who receive a drug or a lifestyle intervention? And we see there on the right is a 2x2 contingency table. What we're basically doing is we're just counting the amount of individuals falling to each group. The null hypothesis in this case is that the proportions of cholesterol level between drug and lifestyle intervention groups are equal. The statistical outcomes that you receive from this analysis is the chi-squared, that's your test statistic that you'll often see, and the significance of the difference in the proportions between the two groups. This is your p-value. We'll talk about p-values later on and the importance of them and how to interpret them. If the categories are dependent, that means they're paired in some way, then you need to use the McNamara test. So for example, if we're asking what is the proportion of patients with high or low cholesterol level pre and post drug intervention, that means the same individuals have been used or tested or analyzed pre and post that intervention, so they're linked, they're paired, and that's why we use the McNamara test in this case. Okay, the next statistical test that we'll talk about here is assessing correlations. In this case, we're looking for relationships in group data using continuous data sets, referred to as a bivariate correlation analysis. What we're trying to do again is assess relationships between two variables. So for example, what is the relationship between soda consumption and bone density? You have an X and the Y. On the X is like soda consumed. On the Y, you see your bone density. And oftentimes what you'll see is the data presented in this way, and this is a scatter plot. Now, statistical outcomes that we're looking for, the first one is the strength of the relationship. This is your correlation coefficient. It'll fall between -1 and +1. In addition to that, we'll be looking for the significance of the relationship. This is your p-value. Now, as I mentioned before, you have parametric analyses and you have non-parametric analyses. For the parametric, again, normally distributed data, you're using the Pearson's moment product correlation. Your correlation coefficient is R. That's your strength of the association. You've probably seen this. It's important to recognize that this is actually assessing linear relationships. There's a distinction between the linear relationship and what a non-parametric analysis actually assesses. For the non-parametric, you're using the Spearman's rank correlation. The correlation coefficient is then a rho, and what this is assessing is a monotonic relationship, not necessarily linear. I'm going to get into a little bit of discussion as what the difference is between them. To give a few examples of how R sort of stacks up when you have different data sets. On the top left, you see a perfect positive linear relation where your R equals 1. In D, you see a perfect negative linear correlation. As that scatter increases, there's increased variability, your R starts to decrease. Now, as I mentioned, monotonic just means that the data in the X and the Y move in the same direction. A is monotonic, D is also monotonic. Even the curve that you see on the soda consumed and bone density graph, that J shape is also monotonic. They're essentially moving in the same direction. But H is not monotonic. For half of that, the data set is moving up. The other half, it is moving down. Great. So let's talk about linear regression and a little bit of discussion on outliers. For linear regression, what we're trying to do is fit the data to a model. We're modeling, in this case, the linear relationship between two variables. Linear is important to recognize here. We're using a best fit line. In this case, we're trying to minimize the error, also known as the residuals, between the observed and the predicted value through the least squares regression. So you might see a line passing through your scattered data set, and you're arriving at an equation where you can essentially approximate or estimate the average bone density based on the soda consumed. In this equation, M is your slope and C is some constant, could be the intercept. And the variation in dependent variable that's explained by the model is estimated, in this case, by the coefficient of determination. So for a linear relationship, that's actually just R squared. A way to sort of break this down, if you have an R squared value of 0.85, just an example, that means that 85% of the variability is explained by the model. And what these are useful for is that it's helpful to design predictive models, as I described. In this case, you can interpolate an outcome or response based on an explanatory variable. Now, it's important to recognize this is interpolation and not extrapolation. You don't want to extend beyond the data set and what it's able to actually describe. Even though you see a linear relationship there with all these little cookies, it doesn't mean that beyond the cookies there, you don't have a curved relationship. So let's talk about outliers and how this can affect your data. So outliers are observations that are inconsistent with the overall pattern. So outlier that is influential and perhaps problematic is one with a large error, a large residual, and high leverage. So influential outliers are going to considerably affect your model. So what does that look like? You have a few outliers here that don't fit the consistent pattern. On the top left, you see one with low leverage and a large residual. It's a large residual because it is far away from that approximation line, but it's low leverage because its X value is actually pretty low. The second one, we have high leverage, but a small residual. If I do extend that line out, it's probably not too far from where the line would intersect. But it's high leverage because it's further along on the x-axis. And that special cookie on the bottom is high leverage and a large residual. These are problematic. It's further away from the line, and in addition to that, it's further along the x-axis. So what it's going to want to do is take that slope and bend it downwards. Because of these, the extreme values, it's going to try to crank that equation, or crank that line a little further down. These are problematic. Okay, let's move on to assessing independent group mean differences. So this is inference on differences in independent cohorts. So for an independent group comparison, we're assessing the difference in means between two groups. So for example, I might be interested in what is the difference in average cholesterol level between treatment A and a placebo. We might have a random sample. We're separating them into treatments and placebos. What I want to do is assess the difference in the means between the two. Our null hypothesis in this case, the means of each intervention are essentially equal. But what we are doing now is assessing the main effective intervention. So quick note in independence, what does that mean? In this context, independence means individuals of one sample are not related to and do not influence the second sample. Now, for the statistical analyses, we need to pay attention to the number of levels of our independent variables and the statistical outcomes that result from that. So if we have two levels of an independent variable, so treatment and placebo, we're using the student's t-test, and our test statistic is the t-value. If we have more than two levels, that's maybe treatment A, treatment B, and a placebo, then we're using the analysis of variance, and your test statistic is the f-value. Of course, in addition to that, you get your significance of the mean difference, and that's your p-value. Now again, back to this idea of parametric and non-parametric. If you have a non-normal distribution, we are using non-parametric equivalents. So the non-parametric equivalent of two levels of the independent variable is your Mann-Whitney U-test. And if you have more than two levels, then you're relying on the Kruskal-Wallis test. Now, quick note on confounding variables. If you were trying to account for a confounding variable like sex or age, and in that case, what you're using is the analysis of covariance. Okay, let's move into now assessing dependent grouping differences. So this is inference on differences in paired cohorts. We're essentially doing a dependent group comparison. We may be assessing the difference in means between two related groups. We might be looking at first taking the random sample, applying the control, then having a washout period, and then applying an exercise intervention. Or, for example, we may be asking what is the difference in average cholesterol level pre and post exercise intervention. In this case, our null hypothesis that there's no difference in means between pre and post. What we're trying to do is assess the main effect of time of measurement. It's time because it is pre and then it is post the intervention. So in this case, the data might look something like this. You have the individual measured at pre-test, and then they're tested again or measured in the post-test. You can see they're moving in various directions, so we need to account for this because they are paired. Now, in this context, dependent or paired means either the same individuals are tested at several time points or under the same interventions, or the participants are actually matched. They can be matched by age or sex or some other factor similar to that. Now, again, the number of levels or independent variables and our statistical outcomes are important to recognize. If we have two levels of the independent variable there, we're using the paired t-test. Our test statistic is then the t-value. We have more than two levels, we're relying on the repeated measures analysis of variance. And our test statistic, again, is the F value. And of course, we also receive the significance of the mean difference. If we have a non-normal distribution, we're using the non-parametric equivalent. In this case, we have two levels of the variable. We're using the Wilcoxon sign rank test. If it's more than two levels, we're relying on the Friedman test. All right, let's get into a little bit of discussion here on interactions. So we'll talk about the two-way analysis of variance. If you only had one independent variable, that would be one way. But now we're talking about two independent variables, and this is our two-way analysis. So as an example, what is the difference in average cholesterol level between current and experimental drug interventions when considering high or low heart disease risk? In this case, we're assessing the main and the interaction effects of the intervention and the risk. We're asking the question essentially, is there a possibility that there's a difference between the interventions and is it affected by risk? So for instance, we might have two cohorts again, testing controls and experimental. Within each one of those groups, we have low risk and we have high risk. So in the control, they may be at this level for cholesterol level. In the experimental group, it seems that both of them are moving in the same direction. Doesn't matter if they're low risk, it doesn't matter if they're high risk. The experimental group is higher cholesterol level. Now, if there's an interaction effect, it might look something like this. Now, this tells a very different story, and again, emphasizes why it's important to assess interactions. So now, it seems like those who have low risk ends up with higher cholesterol level in the experimental group, but those with high risk actually go down. And so it is important to recognize those interventions when they do exist. If you find that the interaction effect is in fact significant, you need to consider testing the main effects separately in that case. Again, so as not produce misleading results and sort of provide transparency is how that interaction, the interaction can affect your intervention. All right, the statistical outcomes in this case, again, this is the test statistic is your F value, and the significance of that mean difference, again, is your P value. All right, so let's talk now about our alphas and our betas and how that corresponds to error. So we'll talk about statistical error types, type 1 and type 2 errors. A type 1 error is defined as your false positive, or it's rejecting the null hypothesis when it is in fact true. Type 2 error in this case, it is a false negative, or accepting the null hypothesis when it is false. And you can see the classification table at the bottom right. I have two classic examples of this is a type 1 error false positive, when the doctor clearly tells the man that he's pregnant, probably isn't. A type 2 error in this case, a false negative, this woman, the doctor telling this woman that she is in fact not pregnant when it seems pretty clear that she actually is. All right, so how does this actually influence your statistics, right? The acceptable probability of a type 1 error, this is your alpha, will affect the statistical significance levels, while the acceptable probability of your type 2 error, your beta, will affect your statistical power, which is 1 minus beta. I'm going to talk about what this means essentially for both. Okay, so let's talk about the critical alpha in this case. What is the meaning of it? Again, your alpha is the level of acceptable probability of committing a type 1 error or a false positive. This is the maximum risk that you're willing to take in your study design to committing a type 1 error. And alpha is arbitrarily set, but it's very common for it to equal 0.05. It's important because in studies, we need to make sure that we're accounting for the family-wise error rates. By that, I mean that the more statistical tests that are performed to assess a hypothesis, the more likely you are to commit a type 1 error. The reason for this is because, again, remember, statistics is just probability. So the more tests you run, the more likely you're going to find something that's statistically significant just based on chance alone. We need to make sure we account for that. So it is common to reduce the critical alpha a priori at the start of the study, during the study design, based on the number of statistical tests. So for example, we might be observing the main effect of a drug intervention on cardiovascular health through two outcomes, cholesterol level and blood pressure. So we have actually two dependent measures that we're looking at. We need to make sure we account for that, because both the statistical analyses are going to be used to assess the same hypothesis. The same process is actually applied to the analysis of variance when the independent variable has more than two levels. So as an example of this is that you may be looking at a random sample and you're separating them into drug A, drug B, and a placebo. In this case, if you find statistical significance in that analysis of variance, you then need to follow that up with a post hoc analyses, pairwise comparisons between all three of those. You have 3 individual tests, and you can use different adjustment techniques in order to account for that. You have the Bonferroni, the SIDOC, the Tukey, and Holm. This is not an exhaustive list, just only a few examples. But as an example, if we were to use the Bonferroni correction, what we're doing is we're taking that critical alpha and we're dividing by the number of statistical tests, which is 3 in this case. So what that means is now significance, your statistical significance, is at a p less than 0.05 divided by 3, 0.017. We have to apply a more strict criterion in this case to find statistical significance, again, to account for that family-wise error rate. Okay, let's talk a bit more about this p-value. Oftentimes I find that it is poorly understood or misunderstood. So what is the meaning of this p or probability value? We'll talk about the definition of an estimated p-value. So you run a statistical test and you've arrived at some p-value. This is the probability of detecting an effect at least as extreme as that observed in the tested sample. This is important, assuming the null hypothesis is true. So in other words, it is the likelihood of your observation, assuming that the null hypothesis is in fact reality. So results with p-values that are less than your critical alpha are considered statistically significant. This means you have evidence to reject the null hypothesis. Essentially, what this means is that when the observed results are unlikely, we have evidence again to reject the null hypothesis. Lower p-values are better, but statistical significance either is or is not, and this is based on your critical alpha threshold. Just because you have lower p does not mean that something is more significant. But, again, as a caveat, p-values that are near your critical alpha may be considered marginally significant. You'll see that term come up in research studies. I remember something else to recognize is that statistical significance doesn't necessarily mean that your results have practical or clinical significance. I'm not going to go into too much detail about that, but it's something important to remember. So let's go into an example of trying to interpret a p-value. So for instance, if my null hypothesis was that there's no difference in mean cholesterol level between drug and lifestyle interventions, but I run an independent t-test, and on those observed results, my p-value is 0.03. And this is now less than my critical alpha, which was 0.05. So what does this mean? What it's essentially saying is that assuming there is no difference in cholesterol level between interventions, that's my null hypothesis, and I'm assuming that to be reality, we would detect the observed difference or something greater in magnitude in only 3% of studies simply due to random sampling error. So what this is suggesting is because that probability is so low and I did just observe that result, I should probably start questioning my reality. So is there evidence now to suggest rejecting the null hypothesis, and maybe I should start considering the alternative hypothesis? Great. All right, so let's go into power and talk about that for a bit. What the meaning of statistical power is and its relationship with beta. So again, remember beta is the probability of committing a type 2 error or your false negative. Something to mention is that there is an inverse relationship between alpha and beta, generally speaking. In addition to that, generally, as sample size increases, your beta is going to decrease. And this is where we get into the concept of statistical power, which is 1 minus beta, in which higher power, higher statistical power, means the more likely the test will reject the null hypothesis, the alternative hypothesis is true. Now, we can actually estimate sample sizes that we need for a particular study by using beta, and these are your a priori power analyses. What we're asking is, how many subjects do I need to detect significance for a given effect size of interest? Now, the estimated minimal sample size, your n, is dependent on a few characteristics. One, what the interested effect size is, and by effect size, what I mean is the magnitude of those differences, maybe between treatment A and placebo. Your predefined critical alpha might be 0.05. The expected data variance, so what is the dispersion amongst my groups? And finally, the predefined acceptable beta. So just as an example, we see a plot here, and I'm plotting sample size on the x-axis. You see power on the y-axis. This is for a t-test. I've set my critical alpha at 0.05, and I'm interested in effect size of 0.7. And you can see as the sample size increases, so does the power, but it begins to plateau. So if I'm actually conducting a power analysis before I go ahead and design my study or execute my study, maybe I only need 60 individuals or 60 participants rather than 100 if I'm going to achieve approximately the same power. I can then, therefore, save some resources and maybe some time. The beta is arbitrarily set, similar to your alpha, but it's commonly equal to 0.2, such that your power, again, is 1 minus 0.2 or 0.8 or 80%. Now, for research, we are encouraged to report, again, the a priori power analysis in our results, right, to make sure that we are actually achieving the type of power, statistical power, that we set out to do in the first place. All right, so let's wrap all this together as we're coming close to the end. What I'll talk about now is ways that you can become the savvy consumer by using the information I provided today in order to evaluate research articles. The first thing I'll talk about is experimental bias, just a little bit here. So these are factors introduced by investigators and or subjects that may influence the results. There are various sources. One might be selection bias. The process of gathering samples is actually influenced. Then there may be misclassification of subjects once they're actually gathered. You have observation bias, where systematic differences exist in the way the data is collected. You have interviewer bias, where the investigator influences the data collection. And you may even have recall bias, where the remembered information by subjects or participants is inaccurate. Retrospective study designs are particularly susceptible and vulnerable to this. Just to give an example of selection bias, I've always enjoyed this example. Let's say, for instance, a captain interviews pilots following their return from battle to identify where to add armor to plates for avoiding fatality. So the captain might ask, where does the enemy attack from most often? Pilot responds, well, from above and behind. So as a result, they reinforce armor on those sections of the plane, but this didn't seem to change the result. Didn't change the number of fatalities. Why was that the case? So below and behind may not have been less frequent, it's just that it was more effective. We had a selection bias, because only the survivors were interviewed in this case. All right, so let's talk a little bit about the steps regarding narrative evaluation or becoming that savvy consumer of clinical research. So these are questions that you need to ask as you're going through literature. First one is classification. You need to know, was it collected retrospectively or prospectively? Was the research meant to describe, assess relationships, or evaluate differences? Was the study design experimental or non-experimental? What are the dependent and the independent variables? For step 2, we need to understand the purpose and conclusions. Does each study purpose have a conclusion? And does each conclusion have a purpose? Are the significant results interpreted along with their practical and clinical relevance? And are non-significant results evaluated for statistical power? In addition to that, also mentioning their practical and clinical relevance. For step 3, we need to understand the designs and the controls. What was the study design? What was the research setting? Was it in a laboratory or a clinic? How were participants selected? Again, is it randomized? Was it purposeful, or was it based on a convenience sample? How were participants assigned to groups? Was it random? Was it systematic? And again, were the interventions actually blinded? Was it single-blinded or double-blinded? For our fourth step, there's a lot of questions in this case. Validity is absolutely critical to a study, again, to make sure that the results are generalizable, that they're valid, and they're not misinterpreted. We need to ask questions such as, how many levels of the independent variables were tested? Was there, in fact, any potential for experiment or bias? Were there unaccounted for confounders, such as treatment interaction and time or measurement technique? Was there participant attrition? Were statistical analyses appropriate based on the information I've given you here? Was statistical power adequate? Was the error rate accounted for, that family-wise error rate that we discussed? Was every participant's data analyzed regardless of compliance? So that's your intention to treat analysis. For step 5, we need to understand the context. So do the study results confirm or contradict other literature findings? Does the study address limitations of previous work? Are the studied variables or interventions novel? Are the sample sizes and the characteristics, in fact, comparable to other studies that you've read? And is the internal and external validity also comparable to other research studies? And then finally, we have utility. This is also very critical. So in this case, you need to ask, are the results actually generalizable, such that they can be applied to your research or clinical practice? Does the study perhaps introduce questions regarding your assumptions and how you actually manage patients? And then finally, do the methods suggest techniques for improving your research or modifying your research or your clinical practice in this case? I'll point you to the Consolidated Standards for Reporting Trials, the Consort checklist. The website is there at the bottom. It provides a checklist on some of these concepts that I described here on ways that you can sort of interpret and evaluate research articles or study designs as you go through them. I highly recommend checking this out. All right, that wraps things up. So here are a few of the key references that I used here. One in particular that I really enjoy is Statistics Without Tears. I can't say I didn't cry while reading it, but that was mainly because of tears of joy. And I appreciate your attention. My email addresses are there. If you want to get in touch or have any questions offline, please don't hesitate to get in touch with me. Thank you very much for listening. I appreciate it.
All right, thank you very much, Dr. Major. Let me try and turn the controls back over to myself. And can you see questions and answers at the bottom of your screen? Dr.
Yes.
Major?
Yes,
Okay.
I can.
Okay, great. Did anybody have any questions for Dr. Major?
Yes, it looks like there is one question.
Excellent.
And the question is, what if you accidentally used parametric and non-parametric analyses when you should have used the opposite? So, excellent question. And it is absolutely critical. And part of the reason is because if your data, for instance, is in fact non-normal, and you are making assumptions on normality, the results that you receive could be exceptionally misleading because the underlying mathematics of making those assumptions on linearity, on normal distribution are critical often to the statistical results and have a huge effect, not for all of the parametric analyses, but a good portion of them. So in that case, you may arrive at a conclusion and say there actually is a statistically significant difference between treatment A and treatment B or placebo, when in fact it might not be, right? So you have really an increased potential for error. Those are the type of things that we want to avoid. So again, for many of those parametric analyses, those underlying assumptions of linearity are absolutely critical because that parametric is making assumptions on the parameters of your variables. Again, as a caveat, some of those studies, some of those parametric analyses, do not, they're robust in such a way that linearity or normal or non-normal distributions won't have as much of an effect. But again, you're making those assumptions and you're adding that into your statistical analysis. So if you are relying on those results to then make, derive conclusions and perhaps even change the way you manage patients, that could be really, really important. Okay, so I have another question. How many outliers can you exclude before it makes your study look fishy? I think inherently all studies are fishy. It's all a bit of an art form. But this idea of removing or excluding outliers is something that you have to make on a case-by-case basis. There's a few ways that you can go about it, actually. When you're actually assessing for outliers, there are statistical analyses that you can use to identify how much of an outlier the outlier actually is. So in this case, if you have a certain amount of dispersion, you have dispersion that you are quantifying with your standard deviations or your confidence intervals, whatever it might be, standard errors, you can identify exactly where that outlier actually lies relative to your data set. So how far away from your data set or how inconsistent it actually is. There's a few guidelines that you can follow. So for instance, if it is 3 standard deviations away from your mean, that might be sufficient evidence for you to remove that outlier. Now the issue in this case is that when you're removing outliers, you have to have a justification for it. You have to go back to your data set and understand what it is about that particular sample which made it an outlier. If then there is sufficient justification to remove it, you can go ahead and do that. But then within your reporting, you have to indicate and explain why you have removed the outliers, whether it is based on some very strict criteria that you had for your statistical analysis, or there was something particular about that sample within that data set, which would suggest that this outlier is something you didn't expect, and it is manipulating or changing the data in such a way that is worth not considering. And oftentimes you'll see in research studies is that you may have an analysis that is done with the outliers and without the outliers. Sort of engenders confidence in your results. But again, in terms of this fishiness, it would be more fishy, I suppose, if you did not explain why the outliers were removed, simply making your analysis look better or to arrive at statistical significance because you removed an outlier really isn't sufficient justification, so you need to be very careful on how you do that. Thank you for the fishy question.
Thank you, and I had a question sent to me. Any thoughts on Bayesian analysis as compared to frequentist approach?
Sorry, repeat that for me.
Any thoughts on Bayesian analysis as compared to frequentist approach?
Yeah, so that's actually getting a little bit in, they're great questions. It's actually getting a little bit into more of the advanced statistics. And, you know, there are pros and cons between each of them. And I actually, in fact, if the person who's sending you that question wants to chat with me a little bit offline about that, I'm definitely happy to do so. We can talk about essentially there's two different approaches and more than two different approaches essentially to statistics in that case. So that's again, a great question, but I think, you know, again, I'm happy to return and talk about more advanced statistics if you want, and that's something we can get into.
Thank you. Are there any more questions for Dr. Major? All right, with that being said, I want to thank you all today for joining us. For more information about the ACNM, please visit www.acnmonline.org. Thank you again for joining us today.
Thank you.
Thank you.